sometimes we can, instead of using our tree diagrams and then calculating all of the different probabilities possible, we can organize these probabilities in a probability distribution. Specifically, these are a discrete probability distribution. The reason why we'll talk about in a little bit, but a couple different definitions here. A random variable. A random variable in general is a variable whose values are numbers determined by the outcome of an experiment. A true probability distribution is a function which maps each value of the random variable onto its probability. I'm not going to write that down. However, the probability distributions that we will be working with are considered discrete. And that's because all of the probabilities add up to 1. Okay, so right now this is just a bunch of words. You haven't seen anything, so you're not exactly sure what I'm talking about, but it'll make a little bit more sense. So when we're looking at a probability distribution, it's going to be set up as a table. It's going to be set up in X and then P of X. And I'm just putting some random numbers down here just to make it a little bit easier. The book will actually have you talk about different specific outcomes, and you'll actually be able to calculate those probabilities. But for now, just to keep things moving along, I'm just making stuff up. So say the probability of getting a 1 is 0.2. Say the probability of getting a 2 is 0.35. The probability of getting a 3 is 0.25. Probability of me getting a 4 is going to be 0.2. Now, if I were to add all of these up, you would see that you'd get 1.0, which is our overall goal. That's how we know that it's going to be a probability distribution, because the sum is 1. Okay, so how does this help? This helps because we can now compare distributions based on their expected value. Okay, so an expected value is the mean of the probability distribution. And there's the fancy formula in order to find that expected mean. This is what we call mu. It's the Greek letter. So mu is found by taking, oh, that's bad, by taking the sum of xi times p of xi. The summation is when we're going from n and then I equals 1. So, okay, I know this formula looks really kind of scary, but it's really not that bad. In order to find any type of mean, we take our values, we add them all up, and then divide them, right? Well, with an expected value, we take our x value times our probability, and then add those up. See, the Greek letter of the big capital E, this is actually a summation. So it's really not as scary as you think. So we take 1 times 0.2 plus 2 times 0.35 plus 3 times 0.25 plus 4 times 0.2. This is going to calculate our expected mean. So this gives us 2.45 is our expected value. So this means that most likely the theoretical value that I would get if I were to do this about 100 times, you know, whatever, would be 2.45. So that really means that if I were to truly do this experiment, whatever it is, if I'm drawing a 1, a 2, a 3, or a 4, I'm more likely to draw between a 2 and a 3 because my expected value, aka my mean, is 2.45. Sometimes your probability distribution is drawn out like a histogram, in that you have the height of the bar is going to be your corresponding probability. That's something we'll look at, but most of the time it'll be set up in this table in which you will figure out whether or not you even have a probability distribution, aka you got to find the sum, and then they'll ask you to find the expected value. So this tells me, again, the expected value tells me if I were to conduct this experiment, you know, 1,000 times or whatever, most likely I'm going to get 2.45. In this case, I can't get a 2.45, so I'm going to get most likely most of my answers will be between 2 and 3.